Hello everyone, and welcome to today's lecture on cycloalkanes, where we'll be discussing the geometry and ring strain associated with some of the smaller ring systems. So cycloalkanes play an important role in both nature and in synthetic chemistry and in pharmaceutical chemistry. And you'll see 5- and 6-membered rings in a lot of natural products and in a lot of drug compounds. Part of the reason for this is that they allow us to impart rigidity into a structure, so it's not quite as flexible as the straight chain alkanes that you see. And we're going to talk a bit about why that is and what these molecules look like. So the molecules that we'll be focusing on today are cyclopropane, cyclobutane, cyclopentane, and cyclohexane. There are larger rings than the 7, 8, 9, and larger ring systems are also important, but they have different energies and strain energies associated with them and other things going on. So if you want to learn more about those, come talk to me in physical organic chemistry. Right now we're going to focus on these 4. All right, so the easiest 2 rings to make are cyclopentane and cyclohexane. The smaller rings are much more difficult to see and less common in nature. And chemists for a long time wondered why that was. And when you draw them, you can kind of see why that is if you think about the standard geometries that we expect around a tetrahedral carbon. Right? So the ideal geometries for a tetrahedral carbon So let's just take butane as an example. All right, so we would expect a 109-degree angle here, 109.5, and we would expect that we would see dihedral angles of 60 degrees. So 60-degree dihedrals, 109.5 degree angles for bonds. So with that in mind, those are our ideals. Let's take a look at what we see in our cycloalkanes. So another thing to note in this convention is that our cycloalkanes are drawn as planar structures in our our line drawings. And if we think about them as planar structures, then we can think about them as simple geometric shapes. But this has some issues with it, and that's what we're going to talk about. So as we draw them, they are flat. But in reality, they are not necessarily so. So when you see a representation that is a 2-dimensional drawing of these, you need to start thinking about them as their 3-dimensional structures. And hopefully this will help you get there. So let's talk about what these would look like if they were flat molecules or flat structures, right? So let's get that back up here. All right. So as a flat structure, we would expect the angle here to be roughly 60 degrees for cyclopropane, good old 90 for cyclobutane, 108 for cyclopentane, and roughly 120 for cyclohexane. So based on this, if we were looking at these as flat structures, we would expect that cyclopentane is the closest to the ideal bond angle for a tetrahedral and therefore would be the most favorable. And we can assess this through heats of combustion. So we'll go back to John Sorensen's video on alkanes if you need a refresher on heats of combustion. But if we look at the heats of combustion for these molecules, we see that this is, and these are in kilojoules per mole. Always keep your units. 1091, 721, 3291, and 3920. All right, so you can see that these are increasing, but so are the number of carbons in our system. So we can't directly compare the heats of combustion of systems that have different numbers of atoms and electrons. So therefore, we have to normalize this, and we can do that by talking about delta H of combustion per CH2. CH2, right? So if we just normalize these per CH2, and again keep these in kilojoules per mole, we will see that this comes out to 697, 680, 658, and 653. So per CH2, cyclohexane has the lowest heat of combustion, which means that this is the least strained of our systems. Now, that is not consistent with the flat structures that we've drawn here. So how do we explain that? Well, we have to go through and actually look at these molecules, and that's what we're going to do now. So to help us with this, I've pulled up some structures, and I would again encourage you to build these with your model kits. The first one we're going to look at is cyclopropane. All right, so we can see a model of cyclopropane here. Now, cyclopropane is in fact a flat structure. You can't bend a three-membered ring, right? So what we see here is that we do in fact have a 60-degree angle between our atoms. Oh, All right, and we can also see that all of the hydrogens are eclipsing. So no matter which way we turn it, this molecule is flat and all of the hydrogens eclipse one another. So we both have angle strain and dihedral, or what's sometimes called torsional strain. So this molecule has a lot of strain associated with it. And if we come back up here, we can see that this is consistent with this molecule having the largest heat of combustion per CH2. All right, so then if we take a look at cyclobutane, right, so as drawn, if it was flat, we would see that again all of the hydrogens eclipse and we would have 90-degree angles. But what in fact happens is that the bond angle shortens. So we'll see something closer to 88 degrees in a cyclopropane, or in a cyclobutane. So cyclopropane, just to summarize, flat, fully eclipsing hydrogens, and 60-degree bond angles, right? If we look at cyclobutane, what we end up seeing is that it is in fact not 90, but closer to 88 degrees. And this comes from a puckering. So it looks, in fact, more like this. So you can see here that this is not flat. It's bent out of plane. And the reason for this is, while this is further from our ideal 109, it does allow the hydrogens to not be fully eclipsing. Right? So of our hydrogens. So here we can see that the hydrogens are no longer fully eclipsed. Right? They take on an angle of closer to 22 degrees, which gets us somewhat closer to our ideal 60. So it takes a penalty in terms of bond angle in order to decrease the torsional strain or dihedral strain from fully eclipsing hydrogens. So this is actually a puckered molecule. All right, our next one is cyclopentane. So we'll close these off here. So again, if we were to draw cyclopentane flat, again, we have the problem of all of the hydrogens being planar. Now here, we would get something closer to 108, which is very close to 109, but what we end up seeing in cyclopentane is that the bond angle here is in fact 105, not 108. So again, further deviation from ideal. This comes again from the fact that we want to avoid fully eclipsing hydrogens. So the cyclopentane will take on a conformation that looks something like this. So here you can see it kind of flat. This is what we would draw. And if we look at it from a side view, we can see that it takes on a puckered conformation where this one carbon kind of pops out of what could be thought of as a plane. But, this is called the envelope conformation of cyclopentane. And you can see here that if we look down any of the bonds, that the hydrogens are no longer eclipsing on any of our bonds. So none of these end up being eclipsed. So it again takes a slight hit on bond angle in order to relieve the torsional strain of the eclipsing hydrogens. Okay, and so if we look at this, we're getting further closer and closer to ideal. And if we come back to our heats of combustion per CH2, or normalized heats of combustion, we can see that as we're getting closer and closer to the ideal, we're decreasing the amount of energy per CH2. So our final one is cyclopropane, or cyclohexane. All right, so as drawn flat, this would have 120-degree bond angles, but this would be over ideal, right? So this would be closer to an sp2 hybridized system instead of sp3. But when we look at this in a conformation where it can avoid fully eclipsing hydrogens, we see that this actually takes on a bond angle of 109.5. So in a cyclohexane, you can see that if we bend the molecule so that we rotate it, we can achieve essentially the ideal conformation. So we've reached the ideal bond angle. And if we look at our dihedrals, so these four would reach a dihedral angle of 60 degrees, which again is what we would expect for an ideal system or a straight chain alkane. So this one has no angle strain and no torsional strain associated with it. And so this is considered to be the least strained or most ideal cycloalkane. And this is consistent with, again, if we come back up here, cyclohexane having the lowest heat of combustion per CH2 because it has no strain from the dihedrals or the angles. All right, so it is important that we understand how these look and understand that when we're drawing these as flat structures, they are in fact, with the exception of cyclopropane, not flat. The system that we are going to spend the most time with in the next video is in fact cyclohexane, because this molecule can be drawn very specifically, and because it is so robust in nature and in synthetic chemistry, it's important to understand the conformations of this. So we're going to have our own video on the conformations of cyclohexane that will follow this one. So I hope this gives you an idea of what we're thinking about when we're talking about small molecule cycloalkanes, what energies are associated with them in terms of their strain, and why you'll see the 5-membered and 6-membered rings more often than you do the 3 and the 4. And so hopefully at the end of this you look at the 2-dimensional structures that you see and we use as a convention for conveying information and start to think about them in the 3-dimensional forms in which they probably sit most often.